Okay, I want to get back to some notation that we did in the summary back in lesson 1 of Unit 4, and that was this new function notation f of x because it's going to come up here in our warm-up. Remember that the number or the letter or number inside of the parentheses is going to be our x value or input, the independent variable, and what f of x is equal to is the output. This entire thing is the output, which is equal to y. And so the inside the parentheses is the x value, after the equals is the y. So here, when they're asking you for d of 0, they're saying when x is 0, what is the y value? So students like to put a little dot at the actual location. So when the input is 0, when x is 0, where is that falling? Well, it's kind of like 0, comma 2.25. It's up there about halfway between 2.0 and 2.5. And so again, they're just asking you for the y value when the x is 0. Let's go do d of 12. Okay, how'd you do? Go out 12 and up. About where do you think that's falling? Again, when it's not on a corner, do your best to estimate. Do you think that's at like 1.90? Do you think that's at 1.8? I'm sorry, 0.9 or 0.8, because it's not at 1. It's not quite on the corner there. Now, solution to d of m when it's equal to 1. Now this is an output that's being given to us. So we follow the output along and we find the input at that place. So we're going to be looking at this spot right here on the line. And so where do you think that is? 8, 9, 10, 11. Is that around 11 for the input? And then again, where is the output 0? That's down here. So the input is 20 when the output is 0. So the answer is given as an x value. 11 is the x value. 20 is the x value when the input is equal, when the output is equal to 1 or 0. Okay, so how are you doing on those input-output questions based on a graph? Let's look at this next one. A toy rocket and drone were launched at the same time. Here are the graphs that represent the height of two objects as a function of time. Can you look at the graphs and decide which one is the rocket's path and which one is the drone's path? Okay, hopefully you were like, okay, a rocket would go just kind of up and down, but a drone actually has the capability of staying flat for a period of time. So the drone is the one that has that flat part. Hopefully you were able to deduce that. Analyze the graphs and describe this as precisely as you can. Now, this is really you typing something up in your own words, writing something up in your own words. So for example, please don't just copy down my words, but write something along the lines of what each one is doing. I could say that the rocket is the curved path. It started at a height of around 25. Do you see that right here? That the rocket's starting right here. It went up to a height of about 45. And then it went down back to 0 after 5 seconds. I mean, this whole path took only 5 seconds. Then you're going to do the same for the drone. The drone went up at a constant rate. See that linear piece? Until 2 seconds, when it stayed flat, until 5 seconds, when it started back down at a constant rate. You see that slope, that linear slope, until 7 seconds. So the path of the drone took a total of 7 seconds. The path of the rocket took a total of 5 seconds. The drone started at 0, went up and down and ended at 0. The rocket started at 25 feet, went up, went down, and ended at 0. So you could say anything about that in your type up. You're just describing the two graphs in your own words. So please take a minute to put this into your own words, the description of that rocket and that drone. Which part of the features of the graphs show important information about each object's movements? List the features or mark them on the graph. And so this is where we go back to this picture and start marking things up that are important features, like the starting point of the rocket, the max height of the rocket. The starting point, by the way, is called the vertical intercept, and also known as the y-intercept. Down here, the ending point is the x-intercept, also known as the horizontal intercept. We could say that the graph was a curve. We already said that in the other comment. So those might be the only important. I mean, there's a downward slope here and an upward slope here. Then if I go talk about the drone started at this horizontal intercept and ended at a horizontal intercept of 0. So we could say that the height of drone began at 0 and ended at 0. This one went up at a constant rate and down at a constant rate and stayed at a flat max the entire time. So you're just kind of circling things and writing down what they are. Horizontal intercept. By the way, this one over here is both the vertical and the horizontal because it's both the x and y intercept. Again, I don't need you to see my writing because you're just kind of circling and labeling the things that you see are important on this graph, okay? Finally, we're at number 6. Number 6 gives us the picture, and here's the description. Would you actually bungee jump? In a bungee jump, the height of the jumper is the function of time since the jump begins. The function h defines the height in meters of a jumper above a river, t seconds after leaving the platform. Here is the graph of function h, followed by 5 expressions or equations and 5 graphical features. So we're just doing like lines to match these. What would h of 0 stand for? When the input is 0, so starting here at 0, where is my output? H of 0 is up at 80, and that represents our y-intercept, our vertical intercept. So we would connect h of 0 to vertical intercept. H of t equals 0 is down here when the jumper hits back down to 0. Well, that's a horizontal intercept, but in my graph, does that person hit 0? Not in what's pictured. And what would that mean? That would mean the bungee broke. So we really don't want them to hit 0. We're hoping they get lifted back up like they're supposed to. Is it possible when someone bungee jumps for them to go so far down that they do hit the river? Yes, the heavier you are, the lower you're going to go. But in this case, our jumper did not. So the horizontal intercept is not seen on our graph because they never touched that spot. H of 4 is at the time of 4. Where is my graph? And so that would be the first dip in the graph. You got it. That's the first dip. Where is h of t equal to 80? That's up here. That's the highest point that we are, and that's the max. Finally, where is h of t equal to 45? That's out here. And I would follow it down to that x value. That is that's not the first peak of the graph. That's out here. Oh yeah, that is the first peak of the graph. Sorry guys. Drew a little wrong thing here. Let me do this one again. So at 45, if I follow it out, there's the first peak of the graph along that same horizontal line. So you were probably thinking that. I'm like, what is she talking about? You got it. So these ones here are matched now. Just draw those little lines in there in your book on page 171. Now, number one, this goes to the next page. So one expression or equation does not have a matching verbal description. Otherwise, we're going to put all of these with their matching verbal descriptions. So these 5 are going to show back up on the second part of a table. So the greatest height that the jumper is from the river, the height from which the jumper was jumping, the time at which the jumper reached the highest point after the bounce, and the lowest point that the jumper reached in the entire jump. So take a minute to look at those and kind of go back and forth between the pages and see which one would go with which. So our vertical intercept, h of 0, is our height from which the jumper was jumping. All right, the greatest height the jumper is from the river is our max. And that was h of t equals 80. The time at which the jumper reached the highest point after the first bounce, that's going to be where h of t equaled 45, the first peak. That first peak is sometimes called a relative max. And the lowest point that the jumper reached, that's our first dip. All right, so which one is not mentioned? That is the horizontal intercept, known as h of t equaled 0. So that's the one we're supposed to fill in to do ourselves. And we had some fun with this in class. This is called the horizontal intercept. We were like, why would we hit down on the river? And students were being very morbid. Okay, so this would be when the jumper hits the river. That's called height 0. So it doesn't show on our graph, but hopefully it never happens to you. Okay. So now, finally, estimate h of 0 and h of 4, and then estimate the solutions h of t equals 45, h of t equals 0. These are input, output questions. So let's go do the inputs first. Where is h of 0 and h of 4 on this graph? So h of 0 means where the graph has an input of 0, and then we follow it up to the graph, that's at 80. If this coordinate point is 0, 80, h of 0 means what is the y? 80. So we just write h of 0 equals 80. Then what's h of 4? Let's go look on the graph. When x is 4, what's my y? So I go out to 4, I go up to my graph, and it looks like y is about 10. If it helps you to write 4, 10 and see that when the input is 4, the output is 10, feel free to write that coordinate pair. And I think writing the coordinate pair is especially important when we get to these output ones. It means I want to know what x is when y is 45, and I want to know what x is when y is 0. So if I go to a y of 45, it looks like there might be 2 of these, but I'm going to say this is the one they were talking about earlier. So I'm going to say 9 at 9 seconds. So we would say h of 9 equals 45. Again, we're estimating. And then what about 0? There isn't one. Luckily, we didn't hit the river. Okay, as always, I'm going to recommend that you go read through this summary, highlight the important parts. By going through the lesson, we can sometimes robotically just write things down that our classmates or teacher are writing. Make sure you understand the key academic vocabulary in this chapter. What is it talking about in this graph, etc.